My dear students, in today's video I like to discuss another lecture, that is block diagram reduction technique. In my last lecture already I have discussed about the block diagram technique, feedback and its effects. So in today's video I like to discuss about the block diagram reduction technique. Already you know that the block diagram technique is used to represent a system in mathematical model of physical systems, and it is not unique in the sense that for the same system we can draw more than one block diagram. So let us start the today's topic, that is block diagram reduction technique. So already we know that a block can represent a components, that is inductor, capacitor, resistor, transistor, etc. So more than one blocks can be connected in series or in cascade if one block will not load the another block. For example, if we will represent one inductor by a block and capacitor by another block, we can connect the two blocks in series or in cascade if one block will not load the another block. And if there is any loading effects in different blocks, then those blocks can be represented by a single blocks. Similarly, if there is no loading effect in between two blocks or in between two components, they can be replaced by a single block. So already I have discussed about the loading effect in my different topics in different lectures. So still now I want to discuss about the loading effects. So to understand the loading effect, let us take a simple example. If we will compare the digital multimeter and analog multimeter, and suppose we will measure the current in a particular circuit by digital multimeter, then accuracy is high compared to analog multimeter, because the digital multimeter will not load the circuit. It means the input impedance of digital multimeter is very high, and ideally it will be infinity. But for an analog instrument or analog multimeter, the input impedance is low, therefore it has more loading effect. It means when we will connect the analog multimeter to any circuit, it will load the circuit. It means it will draw more current for its one operation. Therefore the accuracy of the instrument is low. So this is called loading effect though it is not required for this topic, still you should know the concept of loading effect. So let us now concentrate our main topic, that is the block diagram reduction technique. So the transfer function of more than one blocks connected in series or in cascade can be calculated by multiplying individual transfer function of each block. For example, to understand this, let us take a simple example, that is a power amplifier stages. Let us assume that the stage 1 transfer function is 10 and stage 2 the transfer function is also 10 and stage 3 the transfer function is 10. Then what is the overall transfer function of these three stages? That is 1000 multiplication of these three transfer function, that is 10 into 10 into 10, that is 1000. So let us now discuss how to solve the block diagram problems by block diagram reduction technique. So block diagram reduction technique generally used to solve the critical block diagram problems. So to solve the critical block diagram problems, first we should know some rules of the block diagram reduction technique. So let us discuss about the rules of block diagram reduction technique. So rule number 1, that is blocks in series or in cascade. It means when more than one blocks can be connected in series or in cascade, then how to replace these all blocks by a single block. So that is the rule here discussed, that is rule number 1, blocks in series or in cascade. So let us assume that these two blocks connected, G1 and this is G2, connected in series. Let us assume that this is your X1 and this is Y1. Then obviously this will be X1 G1 and Y1 is equal to X1 G1 G2. So if we will replace this by a single block, then G1 G2, simply it will be multiplied, the transfer function of individual block is multiplied. So this will be the X1 and this will be the Y1. So same output will get, that is X1 G1 G2. So if this will be G2 and this will be G1. Then again we will get same result, that is x1 G1 G2, and here also x1 G1 G2. So this is rule number 1. Then we will discuss about the rule number 2. So rule number 2, blocks in parallel. So this is one block G1, this is another block G2, this is another block G3. Let us assume that all three blocks connected in parallel. This will be plus, this will be minus or plus, anything you can take. Here it will be plus minus, either plus you can or minus you can take. Here also either plus or minus you can take. Here also either plus or minus you can take. So let us, I have taken here plus plus minus, and this is x1 and this is the output y1. So if we will replace this three block to a single blocks, then what change will occur? So here, what is the output? Here obviously x1 G1, x1 G2, here x1 G3. So y1 is equal to x1 G1 plus x1 G2 minus x1 G3. If we will take common x1, then it will be G1 plus G2 minus G3. So if we will replace these three blocks to a single block, then it will be like this: G1 plus G2 minus G3. So this is the y1, the x1. So this is the rule number 2, that is blocks in connected parallel. Then how to reduce these blocks to a single block. Then next we will discuss the rule number 3, that is moving a summing point ahead of a block. So this is the block. Let us assume that G1, or you can take G, and this is the summing point, this is x1 and this is y1. Let's assume that this is your x2. It is plus minus. So the summing point in the ahead of block, in front of this block, the summing point is present. We want to move this summing point to this side, that is beyond this block. Then how or what change will take place, or how will represent this change? in the block diagram reduction technique. So now we move this summing point to this side, that is here x1 will be plus, this will be minus. So here we will get output, that is x1 g, or you can take g1, x1 g1, x1 g1 minus x2. So if we move this summing point to this side, the output must be same, otherwise the rule is not valid, or the transfer function must be same, otherwise the rule is not valid or not same. Therefore, so here we can take this g1, so here we can take this your x2. So now we'll get here x1 minus x2. Therefore, this will be 1 by g1 and here x2. So x1, now we'll get here x1 minus x2 by g1. Now we can get output, that is g1 into x1 minus x2 by g1. Therefore finally we will get x1 g1 minus x2, because this g1 g1 will be cancelled. So the same output we will get if we will move this summing point to this side and divide by 1 by g1 in the x2 signal, then same output will be getting. Therefore this rule is valid, or this can be changed in block diagram reduction technique when a summing point moving from in front of block to beyond the block. So now let us discuss the rule number 4, that is moving a summing point beyond a block. So this is the summing point beyond the blocks, means behind the block. So this is the g1 x1 plus, let us assume that this is x2 and minus, and this is y1. So here y1 is equal to, here we are getting x1 minus x2, so g1 into x1 minus x2. So if we will move this summing point to this side, then this x2, this is x1, and this is the y1, which is equal to, here we are getting x1 g1 and here we are getting x2, let's assume that x2 g1. So here x1 g1 minus x2 g1. If we will take common g1, this is x1 minus x2. So same output we are getting here. If we will replace this, that is if the summing point move to this side, therefore this rule also valid. We can apply this rule in the block diagram reduction technique solving the problem. So next rule, that is rule number 5, interchanging summer. So it means this is one summing point. Let us assume that this is x and this is y plus minus and this is z. So the output y1 is equal to, let us assume that x minus y minus z. So now we want to interchange these two summers. It means the z will come to this place, y will come to this place. Then the same result will get. So if we will put z here, this will be z and this will be y. The same result we will get, that is y1 is equal to x minus y minus z. Therefore this rule also applicable or valid, that is interchanging of summer. We can also interchange more than two summers, that is 3 or 4 summers, like that. So now let us another rule, splitting the summer. Splitting the summer. We can split the summer, that is split one summer to two summer. Let us assume that this is x and this is y and this is z, plus minus plus. So this will be y1 is equal to x minus y plus z. So now we can split this summer to two summer or three summers. So we can split this summer to two summers. This will be y and this will be z. So this is plus, this is also plus. So now same result we will get, y1 is equal to x minus y plus z. X minus y plus z. Therefore this rule also valid in the block diagram reduction technique. So now rule number 7. Rule number 7, that is moving a takeoff point ahead of a summer. So this is the summer or summing point x1. Just assume that this is the takeoff point. Here this is x2 plus minus here x1 or minus x2. So here y1 is equal to x1 minus x2. This also, this is the takeoff point. Here x1 minus x2 signal also will flow. So already I have explained about the takeoff point, that is the signal can flow in various directions, that this signal can flow also to this takeoff point. Therefore if we will move this takeoff point to this side, then what change will take place, that we will discuss now. So now move this takeoff point to this side. So this is your x1 and this is your summing point. This will be plus x2 here. Obviously this will be x1. So therefore here another signal will come, that is x2. You can get x1 minus x2 here. So this signal x1 is coming. So but previously here in this takeoff point the signal is x1 minus x2. Therefore to make the x1 minus x2 signal, so another signal will connected to this, that is x1 minus x2. So this y1 we are getting same, that is x1 minus x2. So now discuss another rule. Rule number 8, moving a takeoff point beyond a summer. This is the takeoff point. Assume that this is your x1, x2, y1 is equal to x1 minus x2. Now if this takeoff point will move to this side, then what will happen? This will be x1. So here the signal is x1 minus x2. Therefore we have to get the same x1 signal here in this takeoff point. So another signal will put here, that is x2 positive. So now we are getting in this output only x1. So that is, this will be x1 minus x2 plus x2. So x2 will be cancelled. So same signal we are getting. Therefore this rule also valid, that we can apply in the block diagram reduction technique. Then now the rule number 9, that is eliminating feedback path. So this is the minus, this will be x1 y1 and this will be plus or minus. Then if we will eliminate this feedback path, then this will be a single block or simple block, that is g by 1 plus gh. If it will be negative feedback, then it will be g by 1 minus gh. So this rule also valid. Next, rule number 10, that is eliminating forward path. So now if we will remove this forward path, let us assume that this is your x1, then automatically it will be a single block, that is g1 plus g2. If it will be negative, then g1 minus g2. So now rule number 11, removing a block from forward path. So now this is the forward path g1, this is g2, so that this is y1, is x1. Then if we will remove this block from this forward path, then it will be like this. So this is the forward path, the block will come to this position, that is g2, here x1, and here it will be g1 by g2. Now we'll test if we'll getting the same output or not. So here g2, that is g1 by g2 plus g2 plus g2. So which is equal to g1 plus g1 sorry, here the output will be g1 and here g2. So the same output we are getting, that is g1 plus g2. Okay. Therefore, this rule also valid. So similarly, we can remove the feedback blocks from a feedback path. So this is some rules about the block diagram reduction technique. Thank you very much. I will start the problem in my next lecture.